So let's go back to the computer and search for such a DC-DC converter. There are several online stores that have a very good reputation when it comes to selling electronic components. For example, if you are in US, you may prefer to use djkey.com or masterelectronics.com. If you are also, there is newark.com. If you are in Europe or in other parts of the world, you may prefer to use Farnell, which sells in various countries, or RS Components. As I am in Europe, I would probably buy these components from Farnell, but I am actually going to search for this DC-DC regulator using DJkey because simply put, it has a easier to use filtering mechanism. I can actually find the component much faster using DJkey. Of course, we can search for this part here on DJkey, and then we can simply go on other distributors like Mouser and Farnell to see what other parts there may be that are not stocked by DJkey, or if we can find the same part on the other online stores. On DJkey US, we have DC-DC regulators all the way down here in the integrated circuits category. As you can see, we have about 377 pages with about 50 records on each page. So there are quite a lot of DC-DC regulators out there. If you were to look on Farnell, we have the same components more or less listed in semiconductors IC, power management, and then DC-DC converters, where we have about 4100 individual components. Now we can simply start to filter these components by selecting to only see what they have in stock, and then we can simply start with the input voltage. Now, as we plan to use only 2 supercapacitors on the battery, we have to select a DC-DC regulator that can work with a very low input voltage. It would be great if it could be 0.3 volts, but I doubt it. But it also must accept at least 4.6 volts, because that's the amount 2 supercapacitors with a maximum 2.3 volts voltage would amount to. Ideally, we want to have a DC-DC regulator that accepts an input voltage above 5.4 volts, so we could use the full capacity of 2.7 volts capacitors, 2 in series. But we can live with 5 volts at the input. So let's go on and select. I probably will speed up this selection because it takes a lot of time. So as you can see, I will stop here even though there are more DC-DC regulators, because 1.5 volts at the input voltage is already too much. I really don't like. I hope there won't be the case that we will have to use a DC-DC regulator that needs at least 1.5 input voltage. So these are enough selections. Now we can go and further shrink this selection by choosing at least 25 milliamps at the output current. And now we can work on the output voltage. As I said before, the UT61E would only need about 5.5 volts, but I want to make this as universal as possible to work on any multimeter or another product. So I want to be able to get at least 6.57 volts out of the DC-DC regulator. At this point we are already down to 3 pages, or about 150 DC-DC regulators, and we can start to think about what kind of DC-DC regulator we want to use. When it, for example, we have to think about the following. DC-DC regulator may work with low voltage, but can it really output 6.57 volts at that low voltage? For example, we see here this particular LM2623 that says it can start at it can work with 0.8 volts input voltage, but because it has a maximum current output of 2 amps, I'm a bit concerned, and I think that it may not actually be able to output 6.5 volts, 7 volts out of just 1 volt. It may be optimized for much smaller voltage differences between input and output voltages. And as you can see, I just went to its product page and opened the datasheet, and we see here at typical performance characteristics this graph, which shows the efficiency compared to different current amounts for an output voltage of 5 volts. And as you can see, at 10 milliamps or 30 milliamps, the efficiency is about the same. Starting with 1.8 volts of input voltage, it will only be about 75% efficient and go up to about 90%. So you can imagine that this IC is somewhat optimized for about 300-500 milliamps, and it's not much better at lower milliamp values. Now also you can see that this graph is only from 1.8 volts and up, so we really can't tell how this DC-DC converter behaves with much lower input voltages. With 1.0 volts it may not even be able to output 5 volts. So just because we have that range of input voltages in this selection, it doesn't mean we can actually output 6-7 volts from low voltages. We really have to check each particular datasheet and see how a certain chip works. Another thing to keep in mind is how efficient it is. And we saw that this particular chip that we have listed here first is only about 75% efficient with 1.8 volts input and output 5 volts. So it's not very good. It's not a chip optimized for low input voltages. Now, another important part when picking a particular chip is we need to know how many other components it requires in order to function. Pretty much all of these chips require at least an inductor, a Schottky diode, and a couple of capacitors. Now, depending on how they're designed, and usually in general, the higher the frequency they run at, the switching frequency, the less requirements they have about the components you need to use with them. So, for example, DC-DC regulator that runs at a high frequency may be able to work with only 2 ceramic capacitors, a small, tiny 4.7 microhenry inductor, For example, let's see this one at 1.7 megahertz. So as you can see, it even advertises ability to run with very small components, such as a 4.7 microhenry inductor, a Schottky diode, 2 resistors, and 2 capacitors, which can be again small ceramic capacitors. DC-DC regulators that work at much lower frequencies usually require larger inductors, and we may not have enough space on the PCB, on the footprint of a 9-volt battery, to fit such large components. Now, another thing that we need to keep in mind is that we should stick to manufacturers that sell their products at various companies. For example, I may not wish to buy Semtech because they're not sold by Farnell, and I'd rather not pay $20 in shipping costs to buy this chip from DigiKey. It's always a good idea to look for a chip that you can buy from several places, and it's always a good idea to see that that particular chip is not end of life, or that it's available in good enough quantities at various manufacturers. Another important thing you need to be aware about is what kind of package this particular chip is in. For example, I may not wish to buy this chip because it has a very difficult to solder package, and if for some reason this part no longer becomes available, I may not find a replacement chip, a chip that has the same pinout as this particular IC. I may wish to stick to a classic 8 SOIC package, which is also relatively easy to solder. There are small adapter boards which can convert this 8 SOIC package into a deep package. Those are easily available on eBay and in other online stores. So, for example, SOIC package would seem like a very good choice. And of course, if there is a possibility to purchase a deep package, that's even better. But most, in general, components that run at very high frequencies are not designed to work in a deep package because, simply put, the pins of that deep package are too big and can cause instability when designing such a circuit running at high frequency. And last, I already mentioned that we should be aware that when we pick a component, we should look at if there are other close enough components that would have the same pinout as our part. We don't want to buy a component and then a few weeks from now we would find out that only the last we bought the last part and the part is now obsolete. This usually doesn't happen in real life, but you never know. So I went ahead and looked on Farnell and RS Components to see what kind of parts I would be able to buy in Europe at much lower shipping prices, and I eventually settled down on this particular IC, LT1307. This LT1307 is available in 8 SOIC package, so it's very easy. Well, it's not very easy, but it's relatively easy to work with. It can output 100 milliamps, so it's good enough for our needs. It runs at a relatively high frequency, so we still can use relatively low small inductors and capacitors. The only small problem it has is that it can work with only up to 5 volts. Now if you go ahead and check the datasheet, There is another good thing about this chip. As I mentioned a few moments ago, these types of DC-DC converters are usually only available as surface-mounted components because of their very small size and because they run at high frequency. Now, this particular part is a bit special because it also is available in a plastic dip package. Not only that, but it's also available as a SOIC package, and we can very easily convert a SOIC chip into a plastic dip chip by using very simple and cheap adapter boards. This chip, as I showed a few moments ago, only works at 5 volts input voltage, up to 5 volts input voltage, but as you can see, the absolute maximum rating says that it can tolerate for short periods of time up to 12 volts. Now, this doesn't mean it would be safe for us to charge the supercapacitors up to 5.3 volts, but it's still a good thing to know. If it's not already enough, there's another beautiful thing about this DC-DC converter. The pinout arrangement is the same as another chip that Linear Technology designs, which is LT1308. So this one also available as 8OIC, but not as a dip package. This particular chip is a bit more powerful. It can output up to 2 amps and is only available as an SOIC package, but as you can see, the pin arrangement is identical. Compared to 1307, this IC can accept up to 10 volts input voltage, as the absolute maximum rating says, but in practice they don't recommend using more than, if I remember correctly, 8 volts. But I may be wrong, so don't take my word for it. I think it's 8 volts. Still, no, it's 10. It's still quite a nice feature. So you may wonder why I didn't go for this LT1308. Well, simply put, I was very tempted by the fact that 1307 is available in dip package, which would make it very easy for someone watching this video to replicate the design onto a prototyping board and play around with this design. In addition, this LT1308 is a bit less efficient when it comes to outputting a high voltage from very low voltages. For example, this particular LT1308 can only output, here we go, can only output, the graphs only show that with an input voltage of 1.5 volts, it can output up to about 200-300 milliamps at 5 volts. It doesn't say how this chip behaves with voltages lower than 1.5 volts. It may very well be the case that it can actually produce, let's say, 100 milliamps with 1.2 volts, but we just don't know. So it's a bit iffy. In contrast, this LT1307 has a maximum output current of 100 milliamps, so it's not quite as powerful as that 1308, but it can actually output those 100 milliamps with much lower input voltages. For example, here we have the output of 5 volts with just 1 volt input voltage. It can actually do 20, 30, almost 40 milliamps with just 1 volt of input voltage. And with just a bit more, it gets close to 100 milliamps, the maximum output power it can produce. The LT1307B variety is even more efficient. It's throughout the output current range, and you can see that with 1 volt it can actually produce up to about 20, 30, 40, 50, 60, 70 milliamps from 1 volt. Now at 7 volts or 6.5 volts we may not be able to output the 25 milliamps using just 1 volt of input voltage, but it's still quite a nice IC. So let's go on and see and read more information about this chip. As you can see, the datasheet is quite long and full of information, and it's very easy to understand how to design the circuit using all the information in this datasheet. Here we have application information and layout hints, which shows a typical arrangement for this chip. As you can see, we have the inductor between the input voltage and the switching pin. We have the Schottky diode going to the output. We have an input and output capacitors and 2 resistors to adjust the output voltage. And that's all there is to it. There are also 2 components here, a resistor and a capacitor, which are for adjusting its internal behavior. It's a bit complicated to explain in a short time, but the previous pages in this datasheet go at length about how to choose those particular resistors and capacitors, those 2 parts. Now if we read on, we can see that we only need a very small inductor, a 10 microhenry one, and we need the only other important part is a capacitor that can be 10 microfarad ceramic if we work with low input voltages of, let's say, 1 to 3 volts. However, if we have a 2 or 3 cell application, which basically refers to 1.5, 1.6 volts, that's usually in a AA battery. So if you have more than about 3 volts, it's recommended to use about 47 to 100 microfarads low ESR capacitors. Other than that, it's quite easy to... The only other important part is the diode, and they recommend going for a 1N5818 as the best all-around choice, or the MBR0520L, which is a surface mount Schottky diode. One important part that someone less experienced with reading datasheets may miss is the fact that the pin 3 is the shutdown pin, which in the case of this particular chip, it always has to be connected to the input voltage in order for the chip to work. As you can see, it's missing in this design, but the datasheet explains on the next page that it has to be connected to the input voltage. There are other 2 pins on this chip, which is the pin 7 and pin 8, which are about low battery detection and so on. We don't care about those. We only have supercapacitors, and we don't care if the supercapacitors get discharged to the... They're not batteries that would be affected if their input voltage goes below a certain threshold. Now, I went ahead and a few days ago and rearranged a bit this design so that it would take a bit less space on a prototyping board, so that it would take less space on the 9-volt battery footprint that I want to use. And here we have the changes. As you can see, it's not much different than the design below. The ground trace, which is this long one where almost all the components are connected, is going under the chip and coming out here to the pin number 4, and I'm planning to simply leave the 2 extra pins we don't use outside the holes or simply cut them off because I don't need their functionality. So these pins won't be soldered onto the ground and output traces. So again, the only thing that changes is the large ground trace that you see here now moves under the chip and on this side of the chip, and the output trace, which is here, now moves on top, and you can see that the Schottky diode, which is now pointing down, the Schottky diode that is now pointing down is now pointing up because it's connected to the output trace on top. You may notice that there is only the output capacitor here. This is because as we have a deep package, it's very easy for me to solder the input capacitor straight across the input and ground, the ground pins of this deep 8 package chip. There is also a small resistor here which connects the shutdown pin to the input voltage through a the resistor is there to limit the current going to the shutdown pin, so that if I want to, by connecting this shutdown wire which goes to a connector, by connecting this shutdown wire to the ground, we can actually shut down the whole chip and turn off the multimeter. Let's say, for example, if I would want to build a small auto shutdown feature by connecting a microcontroller or some sort of device to the jack, to the connector I'm going to take out of the multimeter, out of the battery compartment. Another small change is that instead of just having one R1 resistor here, we're going to have two resistors in series. The R1 will remain a small value, and the R adjust would be a trim pot, a potentiometer, which would allow us to adjust the output voltage from, let's say, 5.5 volts to about 8-9 volts. This will make it easier rather than desoldering and soldering another resistor in place of this R1 resistor. So as you can see, it only takes about 4 or 5 strips of copper on a prototyping board to create this whole DC-DC converter design. Linear Technology, the manufacturer of this DC-DC converter, has a wide range of software applications, and one of those is a free software called LTSpice, which allows you to simulate various circuits. So I took advantage of this and designed the exact circuit that we are planning to put on a prototyping board, and that is also shown here in this datasheet. So as you can see, you can compare it. It's basically the same input capacitor, the same compensation capacitors and resistors, the same 10 microhenry inductor, and just another Schottky diode. This one is through hole, this one that they recommend is surface mount, and we only have another value capacitor of 47 microfarads, because this one is, as the datasheet says, it's optimized for a low input voltage, and I'm planning to reuse this schematic to see if we can output 6.5 and more volts using this chip. And the only other change is that we have here two different values for these resistors. This doesn't change anything. The ratio is still the one for 3.3 volts as the design here says, 3.3.75 milliamps. Basically, it just makes this a tiny bit less efficient. using smaller values for these two resistors. And here we have the 75 milliamp load, which helps LTSpice to simulate how this circuit behaves when a certain device takes power from it. So let's put this LTSpice here and leave the efficiency window there. And we can now go and simulate this circuit. And I'm going to put a probe here on the current taken out of the battery and the output voltage going to the load. You see the current taken from the battery as green and the voltage out of the circuit as blue. So as you can see, in about a second, let me modify this so that we would see a bit more. Let's say 3 seconds. So as you can see, we have about 180 to 270 milliamps taken from the 1.5 volts source, and we have 3.3 volts after about half a millisecond, and then it stabilizes. So now we can simply see how efficient this is. So as you can see, it managed to reach 80% efficiency. Now if you check the graph below, you can see that they are indeed not lying. So 20, 30, 40, 50, 60, 70 is about here, at about 79%. Of course, we have to keep in mind that this LTSpice has more or less ideal components. These inductors, this Schottky diode, the chip itself is not is basically more or less perfect. They don't have flaws. They're 0.01% accurate resistors and so on. If they did this circuit in real life and calculated the efficiency, it's only natural that it would be a bit less than our perfect example here in this SPICE application. So let's go on and modify this and see if we can actually obtain 6.5, 6.7 volts. And I modified here the formula to make it easier to determine the resistor values. So for, let's say, 6.7 volts output times 82 minus 100, we need 450 ohm resistor here. And we are only interested in about 25 milliamps load. There's no point in asking for 75 milliamps when we only need 25. And let's go up to 5 volts, the maximum we are advised to use, and see how this behaves at 5 volts, 6.7 volts output, 25 milliamps. So as you can see, it has no problem achieving that 6.7 volts and staying around that value. Let's go a bit more. Actually, let's simulate it for a much longer time so that it's obvious what happens. Oh, I think I know what happens. Just a moment. Here we go. So you can easily see that the voltage, once it goes to 6.7, it simply stays around 6.65, 6.75, and with green we have the current taken out of the battery in small pulses to replenish the inductor, the energy in the inductor. You can see that we have between 0 and 300 milliamps taken out of the battery to output 6.7 volts, 25 milliamps. I'm not sure that we can still see the efficiency. No, we can, because we have to leave this checked. So let's run the simulation again. And as you can see, we have 90% efficiency. Now let's see what happens if we try to decrease the voltage down to, let's say, 1 volt, which is the minimum this chip is supposed to output. So as you can see, it takes quite a lot of time to even achieve about 5 volts at the output. If I read correctly, yes. It needs about 10 milliseconds to achieve 5 volts output from 1 volt at 25 milliamps load. But we actually wanted 6.5 volts or more, 6.7 volts, using the two feedback resistors. The regulator is supposed to output 6.7 volts, but it's simply not possible with such a low input voltage. So we can try to increase the input voltage, and let's see what if it's possible to do it with 125 volts. So even with 1.25 volts at the input, this DC-DC converter is only able to output about 6.45 volts. So if we just decrease just a tiny bit the current load on the output, we may be able to get 6.7 volts from 125 volts input, which is quite okay. As we determined, 25 milliamps will be probably the maximum any multimeter would ever take from a 9 volt battery. So considering that on average a multimeter will not exceed 10 milliamps even with backlight and several features enabled, we should be fine with this DC-DC converter. Let's go and make a couple of measurements with just 10 milliamps to see what's possible. So let's decrease to 10 milliamps. And first let's see if it works at 125 volts. It should work without any problems. And indeed it does. It actually achieved 6.7 volts and the simulation stopped, and now we can see that we can measure the efficiency, which is 72.9%. In a real world we maybe are going to have about 70%, which is still fine. So let's try with with lower input voltage. Let's say 1.1 volts. And actually I'm going to lower this capacitor because the simulation will be a bit faster. So now at 1.1 volts you can see that the DC-DC converter can only peak to about 6 volts. So we're still just 1.1 volt is a bit too low for to output 6.5 volts. Going to stop the simulation and raise it just a bit, the input voltage. One 1.15 is still not enough to output 6.7 volts, but it can actually do about 6.4 volts. Not a problem. So at 1.22 is the voltage, the input voltage is finally enough to get the circuit stable and be able to determine the efficiency and everything we need. %, 122 volts in, 6.7 volts at 10 milliamps. So as you can see, this DC-DC converter is pretty good for our needs. As we'll only use even less than 10 milliamps, we can be sure that the supercapacitors will be used to quite a large degree. From 5 volts down to 1.22 volts, 1.20 volts, depending on how the multimeter is used, will be just fine. The efficiency is also pretty good for a boost converter, so it's really not a problem. And if we need better efficiency, we can always choose another DC-DC converter from Linear Technologies set of boost converters, or basically any other DC-DC converter that will be available in that 8 SOIC package.